Hello, this is the Exam 1 review slides for spring 2020. So we're going to be going over the free answer portion. For Exam 1, the multiple choice section will actually be on concepts throughout the slides. So take a look at the slides and let me know if there are things that you do not understand with that. So first up, with that, so formal charge, so I have a molecule and I have a couple of atoms indicated, and you need to tell me the formal charge, not only of the atom but also of the overall molecule. We'll get to that in a second. So for this one, what you want to do is, so for this atom, all right, we're looking at this oxygen. These lone pairs are going to go with the oxygen, but each one of these bonds gets cleaved. So when we're doing the accounting, right, we can't double count. So we say formally each one of these, one electron from each of these bonds is going to go on to that oxygen. And so the oxygen now looks like this. One electron from each one of those bonds, and then its lone pair. Right? And so oxygen, if you count over, oxygen is going to have, it's going to want to have six valence electrons. But what does it have now? Well, you subtract what you have now, the 5 here, and so it ends up being +1. So the oxygen has a +1 charge, and if there were several of these, what you would do is then add them up. And because what you're going to do is you're going to assume that everything else is 0. You add them all up. In this case, it's just the 1. So the overall charge would be +1. So for hybridization, right, what we're looking at is lone pair sets plus bond sets. Okay, and so for this carbon here, the we don't have any lone pairs, but we do have 2 bond sets. Okay, 2, and so that means we're going to need 2 letters. And so we start off with S and then add P's to get the right number of letters, and so this would end up being just SP. Now for this one, right, we have, for this oxygen, we have 2 lone pair sets, and then we have 2 bond sets. Okay, so in this case, we're going to need 4 letters. So it's SPPP or SP3. Now, if I were to come in here and say that carbon there, one of the first things you're going to need to do is remember that, hey, there are, in fact, because on this carbon, right, there's only 2 bonds shown, so there has to be 2 hydrogens on there. Okay, and so for this one, no lone pairs, but 1, 2, 3, 4 bond sets, 4 letters. So it ends up being SPPP, so SP3. So don't forget the hydrogens. Okay, so for this one, right, we're going to be looking at a particular bond. So in this case, it's the carbon-oxygen double bond, and there's always going to be 1 sigma bond laid down between the two hybrid orbitals, and then on top of that, that's when we add the pi bonds. And so for this is a double bond, one of them is going to be sigma, and then we add up how many, add any additional bonds are going to be pi bonds. So this one is 1. So we have 1 sigma, 1 pi. That's what makes the double bond. So for this one down here, this sulfur carbon bond, right, we're going to have always going to have 1 sigma bond, but it's just a single bond, right? So we can't have any pi bonds, so it ends up being 0. So you're always going to have 1 sigma bond, and then you're only going to have 0, 1, or 2 pi bonds, depending on how on if it's a single, double, or triple bond. Okay. Now for the condensed structure, okay. So for that, so we're going to be looking at this. There's a couple of different ways you can do this, but the way that I like to is to say, okay, this sort of main chain of carbons, right? Just go ahead and write those out. Carbon, 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 carbon. And then off of carbon 2 here, there's another carbon. So since it's coming, it's branching off, right? We're going to go ahead and draw that bond. Okay. Now, this one here has 3 hydrogens still on it. You can assume that there's a single bond. Off of this carbon here, we have a single hydrogen plus this CH3. These CH are like that. Now you could have put that above. It's not that big of a deal. For this one has this CH, a double bond, another CH. This one here has a CH2, and then you can assume, and then you have the OH. Now there's a couple other ways you can do this. You can kind of mix and match, so it would look like this. Okay. You can also write it as CH3, CH, CH3. So this indicates that all of that is attached here. CH, CH, CH2, OH. Now don't write it CH3O. That's something different. So you got to have the OH together. Or you can kind of mix and match these. That's fine. Either way. Now for the skeletal structure, right? So I always say go in and remember to circle any OH or OH, NH things, hydrogens that are not bonded to carbon, because you're going to need to draw those. But these you will not. Okay, so the easiest way to do this is to just make dots where the carbons, resketch the molecule with carbons, and then add your bonds, right? 1, 2, 3, 1, 2, and then double bond O, and then O, and then H. Now you could do just OH, you could condense it, or you could leave it like that. That is not a problem. We don't have any hydrogens, so there we go. If you wanted to do a sawtooth, right, it's going to be 1, 2, right, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 carbons, 2, 3, right, 1, 2, 3, 4, 5, and then OH. Now this, you have to remember, so I usually draw a triple bond as a sawtooth, but if you were going to be really technical about it, what you would do is you have to remember that that's actually at 180 degrees. So it's actually it would actually look like this, because this is SP hybridized, these two are, and so the lobes pointing out are 180 degrees, and so this bond angle is in fact 180 degrees, right? But I like to draw it as a sawtooth, just so you guys, and particularly when you're starting out, because it's easier to see where the carbons are. Because technically you could draw this as if you drew it without the dots, you just all of a sudden have a triple bond in there, and it's kind of, students can have a difficult time with that. But either one of these are going to be perfectly fine. Now if you want to put it in the lone pairs, great. It's a great habit to get into, but I'm not going to count you wrong if you don't. Okay, so for resonance structures, okay, so the first thing you're going to want to do for any of these things is draw on the hydrogens. Now if there's a charge on a carbon, I'm going to tell you how many hydrogens there are already. So this carbon here already has all its bonds drawn. This one I probably wouldn't, on the test I wouldn't, but since there's only 2 bonds, it means that there's 2 hydrogens. And then each one of these carbons here has 3 bonds shown. So each one of these has 1 hydrogen hanging off of it. Now, good rule of thumb is to start with the charge. So carbon here, it has 3 bonds. It would really like a 4th. So it looks to the neighbors. It has to look either here or here. If it tried to look on this side, if it tried to make take, say, these electrons to make the double bond here, this hydrogen would end up floating away. With resonance structures, you can't move around atoms. You can only move around electrons. So what you need to do is look on the other side. This carbon here can't help. So what we do is we say, okay, now can this one help you? Can this one help this carbon out? And sure, stuff like that. And so what we're going to do is instead we're going to move these electrons up. And when we do that, we end up with slide those up. We didn't do anything here, so that stays put. These electrons slide up. This one maintains its octet. This one gains its octet. But now this carbon here has only 3 bonds. So if you calculate the formal charge, now it's this one that has the plus. And so now it's got to find that 4th bond. And so it could go up here, slide this back down, but the problem is that's just the structure. So let's keep going. Excuse me. And so what we do is we say, okay, well, let's slide this one over. Okay, and so when that happens, what we end up getting, so we haven't done anything with that one, so that stays put. We slide this one over, and so it ends up here. So this one gets its octet, this one maintains its octet. Now this carbon here only has 3 bonds, and so if you do the calculate the formal charge, this would be a plus. And ideally what we want to do is then work with this guy, but we already know that it doesn't have a lone pair, it's not part of a double bond, it doesn't have a charge, so it can't help, because again, moving these electrons would break off one of these hydrogens. So we're done. We've gotten to the end of the line as far as the helping out, and so we're done with our resonance structures. Now last we here, so dipole moment. Now it doesn't matter if there's a charge, if there's a double bond, whatever, lots of lone pairs or not. All we're doing is we're looking at the 2 atoms. Okay, so here, right, remember that's a carbon. So for carbon-carbon bonds, those are purely covalent. Carbon-hydrogen bonds, those are basically purely covalent. But for carbon-oxygen, right, oxygen's closer to fluorine on the periodic table, and so carbon's going to have a partial positive, oxygen's going to have a partial negative, right? Because the electron's going to spend more time on that oxygen because it's more electronegative. Same goes with this one. So here, and it doesn't matter that this has a negative charge or this has a double bond. We're just looking at the difference between the atoms. And with the arrows, right? To get the overall, we just split the arrows, and so it ends up being like this, and so you end up getting overall. This is the overall. If you try to do the the symbols, it would be partial positive, partial negative, partial negative. Well, this would be, say, here. So make sure you didn't think it was there. So, okay, good luck.